Well, hi everyone. Welcome for this new meetup of the French AWS user groups. I hope everyone is fine. We'll start today this new meetup. As you can see, I'm speaking in English because all of our speakers are English native or speaking in English. So that's why I'm speaking in English. Today's subject will be about chaos engineering. We'll see how it could help organization to improve the resilience of their systems. And for this, I'm presenting myself. So I'm Julien. I'm working for Devoteam Revolve. I'm in charge of the AWS user groups of Paris, Toulouse, and Montpellier. A quick introduction on the AWS French user groups. Today we have 16 user groups in France, and the three biggest are Paris, Toulouse, and Nantes. Before starting, a quick question. Could you please post on the chat on Twitch where you come from, the city, and also the country, because today we may have some people coming from abroad. So hi to the one not coming from France. It should be your first time. So I just show you on this slide all the little animals we have for every user groups in France. A few links before starting. The first one is a link for the Slack of the French-speaking community. I will share it then on the chat just after my presentation. And another one is the French podcast. So all the podcasts are in French. It's done by Sébastien Stormac, and I invite you to see and to hear two episodes, the 30 and the 24th, that are talking about our two topics of today, about the game days, about breaking an infrastructure just for fun, and another one about operational excellence with Adrian Hornsby, who used to talk about chaos engineering. Two other things. The first one is the broadcast. It's a show that is planned on July 9th. We'll have Patrick Fulop, who is head of public cloud at NGIT, and also Sylvie Houlier-Maïka, who is head of sales for AWS France. So you could just register with the link. And a final one, every Friday, Sébastien Stormac on his Twitch channel is giving you a quiz for certification. So it helps you to train and to have your certification after that. One word, I may have seen him on the chat to congratulate Pascal with the first French AWS hero. We learned that last month, so congratulations to him. Finally, we would like to thank Sébastien for his help. Today we broadcasting the meetup on the new tool, which is StreamYard. So I hope everything is going to be fine. Do not hesitate to tell us what you think about it on the chat also. Finally, the agenda. So today we are very, very happy to have four great speakers. The first one will be Patrick. He's coming from the company Gremlin. Maybe you know it. He will talk about the fundamentals of chaos engineering and AWS reliability. Then we will receive Yan. Yan is also an AWS hero. He will tell us how to apply chaos engineering to serverless application. Then we will have Gunnar. As you can see, he's also AWS hero. And he will talk about verification of serverless applications. And finally, will join us at the end, Adrian Cockcroft from AWS, and he will tell us a story about continuous resilience. So, Patrick, I know that you're already here. How are you?
Hey, I'm well. How are you?
I'm fine. Thank you for being here today. I give you the mic, if I can say, and to everybody. Have a good meetup and see you then. One other thing, do not hesitate to ask all your questions on the chat, and we will take the questions at the end of every talk. See you in 5 minutes. Patrick, you can start.
Okay. Hey everyone, it's great to see you all today. So today I want to talk to you all about chaos engineering and looking at the fundamentals of it and its association with AWS as well. So just a little bit about me before we dive in. My job title is that I'm a chaos engineer at Gremlin. This essentially means that I advocate for chaos engineering both internally and externally, and also think about the easiest ways for people to get started with chaos engineering using Gremlin. Prior to my current job, I was working for Elizabeth Warren's presidential campaign for a while. And prior to that, I was actually a software engineer at Gremlin for a time. A fun fact about me, around 10 years ago today, I actually moved to Paris and worked as a bartender in Cockcroft for about 6, 7, 8 months, and played football up at Saint-Denis as well. I had a really good time out there. I'd love to come back sometime soon. It'd be really good. So I want to get started by just level setting and thinking about this outage that was a pretty big one for AWS that occurred in 2017. Essentially, a engineer at AWS was looking to cycle some S3 billing machines and took down a number of critical S3 services. And this impacted a whole bunch of organizations, including Docker Hub, GitHub, GitLab, Bitbucket, Travis CI, and communication tools like Slack and PagerDuty. It was such a major outage that AWS couldn't update their status page. So it looked like everything was fine as well. And that's not to have any kind of like criticism of AWS necessary, but to say that in the current environment that we work in, these failures are inherent to the complex systems that we work in, and we will eventually have situations where downtime is an inevitability, and it should be tested for. So we're currently operating in this environment that's moved from on-prem to the cloud, and that's come with numerous consequences associated with it. Some of them are really good, like decreased costs and lower maintenance potentially, and also the ability to scale quite easily and effectively. The trade-off there has been that we've got a greater abstraction and less control. And one of the results of this is that we've had to think of new ways to build applications. We also have dealt with a move resulting from this from monoliths to microservices. And this has been good in certain ways, like it's increased developer velocity, and it's enabled organizations to scale both in terms of their capacity to serve users, but also in their capacity to build out teams. The trade-off has been that we've gone from the previous environment to having situations where we have tens to hundreds to thousands of microservices. And that's created larger, more distributed systems and additional complexity. So the end result is we've had to think of new ways to test and handle failure conditions and the complexity itself. So at Gremlin, we want to think about this downtime and the inevitable failure that we're talking about because there are quantifiable costs associated with it. The first quantifiable costs are revenue, so essentially your ability to serve users. That's a very explicit and obvious one. There's also employee productivity. So obviously, if employees are fighting fires, they're not building new product for you or trying to mitigate potential complications and situations that they might have in the future. So that's an added cost. And we also have costs after the outage as well, including the potential for customer chargebacks associated with SLAs, or the potential as well for fines if you work in heavily regulated industries. There's also unquantifiable costs, including brand defamation. That can be a pretty huge one. And sometimes it's unquantifiable, and other times it is quite quantifiable. A good example of that is in 2017, British Airways stock lost $75 trillion overnight because of a big outage that they had. So that was quite quantifiable for them at the time. We also have the potential for employee attrition, which is quite hard to quantify up front, but it's a huge part of the equation. So employees don't want to be fighting fires. They want to be working between 9 and 5 and not getting paged at 3 a.m. in the morning. And if employees happen to leave your company because of this problem, it puts the responsibility on the rest of the employees that stay. So it can turn into quite a vicious cycle. It's estimated that Amazon retail loses a lot per minute, $220,000 per minute of downtime. So you can see that as you start to scale, the additional consequences magnify. And for your company potentially, it's estimated that for an average company operating in the tech space, the average cost per hour of downtime is $300,000. So thinking about that, if there's 8,760 hours in a year, if you're looking for 3 nines of uptime, 3 nines of availability, you're allowed 8.76 hours of downtime per year, which in itself would cost the company $2.63 million. So we're dealing with really huge numbers, and the more successful you are, obviously the bigger those consequences will be. So if value is inherent and it costs a lot of money, what are some things we can do? Well, I would like to present the possibility of chaos engineering as a thing that could help you with this solution. So chaos engineering helps in several ways. It helps you identify the weaknesses in your systems so that you can build more resilient ones. And it may help you to avoid some incidents as well. It trains you to identify potential incidents and trains your teams to respond to incidents as well. So let's dig a bit into what is chaos engineering. So chaos engineering kind of sounds like a bit of a misnomer. Essentially, the chaos in chaos engineering is not us applying the chaos. It's chaos that we're looking to discover. So we're looking to really explore and dig into the chaos of the real world and do so in a very controlled and scientific manner. So we want this chaos experimentation to be really explicit. We want it to be methodical, and we want it to be scientific. So we start with the hypothesis, and we experiment to validate that hypothesis or invalidate, however it may be. That means that we want clearly established steady state based on the metrics that we have associated with our system that we're dealing with. So we want to establish steady figures when it comes to throughput, error rates, latency, and the other metrics that are associated with our relevant outcomes. And we also want to make sure, obviously, if we want these metrics, it's really important that we have good monitoring tools and an explicit insight into the observability areas that we are interested in. So we want those to be associated with the systems that we're looking to test. We also, it's really imperative that we start small and increment. So we want to start with like the smallest increment that'll yield a potential signal in our monitoring and alerting. And we want to move safely from a small scale to a larger scale as we go. We can also kind of move from environments that are more comfortable to environments that we're a little more nervous about. So we want to move through these environments safely. So it's good to start in environments like dev or staging and eventually move to production once we feel confident with the experiments that we're working with. It's also really important to think about communication. We want to share our plans with everyone. We also don't want to put other teams in a situation where they're not aware of what's going on. We don't want to negatively affect them because we won't make any friends that way. So this practice, chaos engineering, is all about learning. And we really want to be in a situation where we can share what we've learned with other engineers, both internally and externally. And as we've said, chaos engineering is about iteration. We want to create this hypothesis, run through an experiment. On the basis of the experiment, we want to create tasks that improve our software and/or our processes. And then we want to iterate and try again. So we could update the hypothesis and repeat. As we go through, we can increase that blast radius, we can increase the magnitude of the attack. But obviously, we want to start with these things as small as possible. So at Gremlin, to sum it up, we like to say that chaos engineering is about thoughtful, planned experiments that are designed to reveal weaknesses in our systems. And these systems are both technical and human. So we want to look at where our tech may be somewhat insufficient. Does our user experience have breakages that we don't, that are in the critical path and affecting our user experience? Do we have situations where monitoring and alerting is not up to scratch? Does our auto-scaling work even? It's good to test out those auto-scaling policies. And we also want to test out our retries too. We also want to dig into the human systems and processes associated with our systems. So does our alert rotation work correctly? Do we have the required documentation and playbooks to make sure that we can remediate any potential situations in the most effective manner? And do we have adequate escalation processes as well? So as we go along, things tend to become more complex as we go. And it really is a situation where the earlier you start with thinking about proactively mitigating failure, the better you're going to be at it. There's no time like the present, particularly when it comes to thinking about chaos engineering. So let's dig a bit more into the how. So as we've previously said, we want to start with these initial tests being as small as possible to essentially elicit a signal. And then as we grow comfortable with the way that our system is responding to these introductions, we can then expand the blast radius and continue. And as previously mentioned, we want to operate in a way where we're not just breaking things in production straight away. That's not what we're about, not what we're here for. So what we essentially want to do is move from environments that are more comfortable and move through to eventually into production. This is really similar to how we think about code changes, and it should be something that is relatively familiar to people. You know how to do this. We're just kind of looking at a slightly different method. Obviously, even though we want to start in a development environment, it's really important that we do get to production. That's where our users live. Even though it can sound scary, environments aren't all the same. Things that we test in staging are not going to clearly reflect the way that production will work. So it's really important that eventually we look at testing in production. So I wanted to go through kind of like a few of the vectors that we can look at when we're looking to introduce chaos engineering. So we can think about resource failure, and that might include things like CPU, disk, memory, and I/O. This is kind of like the bread and butter of cloud. We want to check if things like auto-scaling is working correctly. And obviously, we don't want to be in a situation where we have spikes and we aren't confident that things are going to work effectively. We can also think about service failures. So these might be things like killing processes, shutting down hosts, pods, or containers, or potentially skewing clocks. We want to ask questions like, can services restart without some manual intervention? And And is traffic automatically rerouted in situations where things need to be restarted? We want to ensure that our stuff is as robust as possible. And there's also looking at dependency failures. So we want to look at the network. And that might include black hole, DNS, latency, and packet loss experiments. So what happens if dependencies become available? And what happens if the network goes bad? We want to be able to handle these things as well. Obviously, in a cloud environment, this is absolutely crucial. And then fourthly, we want to look at application failures too. So instead of just looking at infrastructure, we can also look at being able to test failure as it occurs in applications. So this might include things like injecting latency into code and throwing exceptions and errors as well. This kind of testing can be really, really useful because you can segment potentially just to, you can kind of slice and dice traffic when it comes to this. So you could segment to specific users, specific devices. It can be really effective and a really good mechanism for looking at testing in production. And we also want to think about a continuous practice as well. So do we have confidence that things are going to essentially be robust and work effectively as things kind of like change within our system? Obviously, our systems these days are inherently dynamic. Things change regularly. Being able to automate through scheduling experiments or thinking about CI/CD is a really good way to make sure that we don't end up with any regressions. So I wanted to kind of think about what we've just mentioned and what we've just been looking at within the context of AWS. And a way to think about that is through looking at AWS's well-architected framework, which is essentially a program that was built by solutions architects at AWS through the experiences they were having dealing with customers. And through looking at that, they really help to guide users and technologists as they look to understand the pros and cons of different implementation details. So you can essentially learn architectural best practices for operating in the cloud environment. And this framework is kind of broken down into 5 separate pillars: operational excellence, security, reliability, performance, efficiency, and cost optimization. So thinking about chaos engineering, 2 of them really stood out for me. Chaos engineering is really obviously a tool that may be able to help you in these particular environments. So looking at operational excellence, the definition that is provided is that it's the ability to run and monitor systems to deliver business value and continually improve supporting processes and procedures. And reliability is the ability of a system to recover from infrastructure or service disruptions, to dynamically acquire computing resources to meet demand and mitigate disruptions such as misconfigurations or transient network issues. So looking at operational excellence, you can kind of see that this is more associated with social and organizational outcomes. And we have these points here that are specifically, I think, related to outcomes we can find through having a chaos engineering practice. These aren't all the points associated with operational excellence, but just ones I picked out. So looking to refine operations procedures frequently, excuse me. As you use operations procedures, you can look, as you look at your operating procedures, you can look to improve them. And as your workload tends to evolve, you can address having to change these operating procedures as well. A good way to do that is to set up regular game days. That's actually suggested by AWS, where you can review and validate that all your procedures are effective and that teams are really familiar with them. So that might be an environment where you have new people come onto the team. That's additional institutional knowledge that needs to be imparted. Making sure that you have all the correct documentation, the correct procedures in place to make sure that your new hires or your employees generally have the tools required to make the best decisions at the right time. In terms of looking at anticipating failure, AWS suggests looking at pre-mortem exercises to identify potential sources of failure so that we can look to reduce or mitigate the consequences of them. And obviously, that is really in line with this idea from chaos engineering of proactively looking and seeking out chaos before it spikes or it pops up for us at times that may not be when we'd like. And looking at learning from operational failures as well. Obviously we want to have a culture that's really like a learning culture where we're learning as much as possible from things that happen around us. And we want to be able to develop a culture of learning these lessons. Chaos engineering is a really good way of establishing those kind of practices. Because it's doing these things in quite a controlled environment when the pressure may be slightly more off than if you're having outages at 3 a.m. in the morning. And then I wanted to look just quickly at the reliability pillar as well. And this is much more technical than it is social. So this seems to fit quite well with the prospect of chaos engineering. So looking at testing recovery procedures. We can obviously do that through using chaos engineering to validate specific failure scenarios. And we also want to look at the potential to recreate different scenarios that have happened before so that we are validating that these things won't happen again. And if we have similar scenarios, we're in a position where our employees and the people we work with are comfortable dealing with those situations. We also want to be able to automatically recover from failure. You can obviously look at chaos engineering as a mechanism for testing and validating that some of this automation will actually work correctly. Potentially looking at chaos engineering as a mechanism to trigger thresholds and make sure that sophisticated remediation around the way that your system will operate is going to be triggered and it'll work effectively. We also want to look at scaling the potential to scale horizontally so that we're aggregating system availability. So obviously looking at whether our scaling policies are working effectively is a good mechanism, is a good opportunity for chaos engineering testing. And we want to stop guessing capacity as well. So, chaos engineering would be a good mechanism there for thinking about how we're going to, what capacity will look like and what we're going to see in terms of how our resources are going to operate, how things are going to be allocated as we move into varied environments and maybe some more challenging situations. And then managing changes in automation. So we want to be able to look at chaos engineering as a mechanism, potentially through CI/CD, to validate any recent changes we've had and make sure that there aren't any potential regressions associated with them. So if you're interested in giving us a whirl yourself, a really quick and easy way to do so is to just look at Gremlin's free edition of our application. Straight out of the box, you can install the agent and run shutdown CPU and black hole attacks straight away. So that's at gremlin.com/gremlin free software. We also have a Slack channel with over 5,000 engineers on it, and that's at gremlin.com/Slack. And that's a really good way to get started too. There's a lot of people on there who are, in a number of different companies with a number of different experiences and stories. A lot of people are servicing different needs, different customers, and they've all got different kind of ways to go about it as well. if you have any other questions, like if something comes up later that we haven't addressed during the session, feel free to hit me up at HiggyCodes on Twitter or at patrick@gremlin.com as well.
Well, thank you, Patrick. I don't see any question for the moment. Thank you for this nice introduction. So maybe we should wait 1 minute. If you have any question, you can ask it directly on the Twitch chat. So there is a first question. Is there an audit tool in AWS tool that assess an application comply with the 5 pillars?
I'm not actually sure if there's an auditing tool. I know that you can go through a review process, and I think that's more more of a discussion, where the auditing process is a bit more of like a kind of like a discursive experience where you talk through implementation decisions. I don't know if anything out of the box is available for testing that. A lot of the things within the framework are kind of they're principles. So I think like having a straight like, you know, like this is a validation of the fact this exists and works correctly might be a little hard for some of it.
All right, I saw that Sebastian just sent the link to the well-architected tool on the chat. Thank you, Patrick, for the answer. Any other question? If not, are you staying, Patrick, for the other talks? Maybe you could answer directly to the chat, if it's okay for you.
Yeah, for sure. I'll stick around. Absolutely.
Right. Thank you very much for your introduction. We'll have now our second speaker. I just show you the agenda once again because it didn't appear before. Hi, Yan. Are you there?
Hey, man, I'm here.
How are you?
Yeah, not too bad.
All right. Well, you have 20 minutes. You can start whenever you want. Thank you for being here.
Sure. Okay, let me just start my slides and then we're good to go. Can you guys see my screen okay? Hey, Sebastian, let me know if you can see my screen and see my slides. Sebastian? Okay.
Yes,
okay.
Okay. So it was working, so you can start.
Okay. Yeah. Perfect. Yeah, because when I start the presentation, I can't see the screen, so I don't know where you guys just see it.
No problem. You're live.
Okay. Cool. Thank you. I guess first of all, thank you guys for joining us tonight, and welcome to this talk on how to apply some of the things that Patrick just talked about in practice to a serverless application. So I guess Patrick already covered what does it mean when we talk about chaos engineering, and I guess for the fact that you guys are here, you probably heard about chaos engineering already, and you probably heard about them from the companies like Netflix or Amazon, how they will kill servers in production at random to simulate different kinds of infrastructure failures that results in the loss of, say, EC2 instances, and see how the system holds up and whether or not they can still stay up when those infrastructure problems happen. It's certainly one way you can apply principles of chaos engineering in practice, but I think chaos engineering itself is much broader. So if you look at the definition of chaos engineering on the principles of chaos.org, which is easily one of the best places to go and read about the chaos engineering if you want to get started and understand its core principles. So it defines the chaos engineering as a discipline of experimenting on a system in order to build up confidence in the system's capability to withstand turbulent conditions in production. And it's becoming more important nowadays. And as Patrick mentioned, we are building more complex systems that are also more capable, but there are a lot more moving parts, which means that we have more complex and hard to predict failure modes. And the more moving parts we have, the more likely we're going to see some form of failure in one of those moving parts. And so chances are we're going to see failures happening more frequently as well. which means more than ever, it's important that we do our best to safeguard the experience of our users when these failures happen. And it's why resilience is such an important non-functional requirement nowadays, and that's for everybody. But what does it actually mean when we say, you have to build systems that are resilient? If you look at the dictionary definition for resilience, it says the capacity to recover quickly from difficulties or toughness. In other words, it's not about preventing failures. And that's important because, as Werner once said, everything fails all the time. And you have no control over when failures happen. All you can do is prepare yourself for when they do happen, and they will. Eventually, everything's going to fail. This can get corrupted, chips can burn out, and people can trip over cables and disconnect networks or computers. And sometimes you lose network connectivity because sharks apparently like to bite those underwater network cables that connects the internet together. As British people like to call it, we call it Sod's Law, but I think everyone else know it as Murphy's Law, that anything that can go wrong will go wrong. And the goal of chaos engineering is to identify these weaknesses in our system where failures can happen before they actually happen to our system and cause system-wide aberrant behaviors. And how we do that is we do that by using controlled experiments to firstly learn about how our systems actually behave when these failure conditions happen. In the same way that we write tests for our business logic, we also need to test our system's robustness and resilience against turbulent conditions that it will eventually face in production, which could be done in a number of different ways. It could be done through organized events such as game days, whereby, for example, you may gather together as a team, and one of you may decide to, you know what, I'm going to turn off networking on one of our servers, and then you see how quickly your colleagues are able to firstly identify the problem, detect that there's an issue, and notice that the problem is that we lost the network connectivity on one of the servers, and see whether or not you have enough monitoring and diagnostic tools in place. Or alternatively, you can do this programmatically by injecting failures into your system and just see how it handles them. Of course, like Patrick mentioned, we don't want to do this in production right away. We want to do this in, say, a dev or staging environment where we can be more comfortable, so that in case we do find a problem, it's not going to actually cause a production outage, because that's not what we want to do here. We don't want to actually cause problems. So my name is Yan Cui. I'm an AWS serverless hero, and I've been working with AWS for a very long time now. I've been running production workload on AWS for over 10 years. The last couple of years, I focused primarily with serverless technologies, including migrating a social network to run pretty much entirely on serverless. That was a couple of years ago, and you can read about that experience on a series of blog posts in the link here. Nowadays, I spend half my time working with Lumigo as a developer advocate. And the Lumigo is a troubleshooting platform for serverless applications, where you can see you have one single place to go to see all of your traces, all of your logs side by side with each other, and you can easily find information about your Lambda function invocations, and then see what are the different things that are used within that transaction. And the other half of my time, I spend working as an independent consultant, where I work with companies all around the world to help them go faster for less by adopting serverless technologies properly. And I do that through trainings, through consulting, and sometimes I work with clients to actually deliver MVPs or projects on their behalf. In my spare time, I've done a lot of blog posts, also video courses. I've done a few things with Manning, and also self-published a few video courses. And recently, I've been running a podcast where I speak with other people who are using serverless in production. So going back to the point about the chaos engineering, I saw this tweet recently asking, well, I mean, what's the point of applying chaos engineering to serverless specifically? Because surely AWS is doing that already against the infrastructure that you're using to run Lambda function already, right? It's a good question, but then again, when you look at everything that is on your stack that runs your application, it's not just the infrastructure, it's not just the platforms and the hardware that's important that can fail. The great thing about chaos engineering is that it can it's not limited to just your application as well. I'm sure you can use it to test your infrastructure or the platform, but you can also use it to test the people and the processes that you have within your organization. And with the great thing about building my application on top of managed services like Lambda is that AWS is doing all kinds of things to make sure the Lambda service itself and the infrastructure beneath your functions and your code are highly resilient. So as a customer, I don't have to worry about a huge class of failures, such as the hardware failures or individual servers dying. All of those are managed by AWS, and they're continuously testing their infrastructure to make sure everything is as resilient as possible. But just as we have the shared responsibility model for the security of applications run in the cloud, whereby AWS is looking after some of that, but you still have to look after security of your own application. The same ideas apply here, that even just because Amazon is looking after the basic building blocks for your application, the underlying infrastructure, the hardware, the networking, and the OS as well, to make sure that they're secure and they're reliable, I am still responsible for my application code. I can still use chaos experiments to identify weaknesses in my code, as well as in my organization and the practices and processes that I have in place there. So in terms of tools available to me, you've probably heard about Netflix's Simian Army, where you have a whole bunch of different monkeys for killing servers, for injecting latency, for killing an entire availability zone or even a whole region. You also have commercial systems like Gremlin, where you can automate a lot of these experiments on your infrastructure and give you a really good user developer experience to manage the experiments you run, to schedule them as well. And also seen other open source tools that allow you to run chaos monkey logic through Lambda function. But ultimately, what about our serverless architecture itself? I mean, we don't have access to the servers that are running our code anymore, so there's no server that we can queue, but there's still lots of different application level weaknesses and failure modes that we can test. For example, maybe I have misconfigured my timeouts, or they're not aligned, so that user-facing functions can time out before some internal API is talking to is timed out. Or maybe I'm missing some error handling, which is incredibly basic mistake to make, but also very, very common in practice. And in cases where, say, a downstream system is having an outage, maybe I'm missing a trick here by not having some fallback strategy in place so that I can return some cached or default response so that I can still continue to operate even when some of my dependencies are failing. So Gunnar, who is going to talk next, and he's also one of the AWS Service heroes as well, he published a very helpful library that allows me to inject failures into a Lambda function so that I can run different experiments against my application. And there are always 4 steps to any chaos experiment. Step 1, you got to know what normal looks like for your system. If everything's on fire all the time, then you don't have a steady state, and you probably need to get your house sorted out in order first and establish what normal working condition looks like in terms of your, say, 99 percentile latency should be below 500 milliseconds, or maybe there should be a certain percentage should be lowered less than a certain percentage of errors per error, for example, so per hour. And once you know what normal looks like, then you can start to really hypothesize, well, what's going to happen if something was to go wrong? For example, if a server dies, or what happens if DynamoDB starts acting up because there's some problems happening within DynamoDB. And then you can inject failures to your application to simulate those conditions that you want to test, but you want to keep them realistic. It's really easy to get carried away once you start doing some of these experiments. And finally, after you run the experiment, you go through the data to look for evidence to either prove or disprove your hypothesis. Here you're looking at your metrics, your logs, your X-ray traces, or any other form of telemetry that you have that you're collecting, and you try to look for evidence that supports your hypothesis about how your system would behave. So, for example, using the failure Lambda library from Gunnar, I'm able to really easily inject latency into a Lambda function invocation. So as an experiment, I may ask, well, what if a service that we depend on is having some elevated latency? How is the application going to cope with that? And a very simple setup would be, we've got some user-facing API Lambda function behind API gateway. And when a user makes a request to this API endpoint, the Lambda function runs. And to do its job, it needs to talk to some other API endpoint that you have, which is also serverless, and it's got API gateway and Lambda behind it. So if you look at this very simple piece of code, it's simple enough. All it's doing is making a HTTP request to fetch some list of restaurants, and then it returns that data to the UI, I imagine. If you look at the code, we actually have some error handling here already, that if we couldn't load the restaurants from this HTTP endpoint, we're going to return some default response, maybe some hard-coded list of restaurants that we know are always going to be available. So our hypothesis is that, well, if something was to happen to this endpoint, then our caller API is our caller function is going to timeout HTTP request, and then the try catch is going to handle this timeout, and then it's going to return some default response, and everything should continue to work. But when you run this experiment, you might find that, oh, actually, it didn't work like that at all. All we got was some internal server error. We didn't get this rendered HTML page. So it turns out that my function did timeout after 6 seconds. And when you look at the logs, you can see quite clearly that, sorry, not 6 seconds, 3 seconds in this case, that we were trying to make the request to this restaurant's endpoint, but we didn't get a response back within the 3 seconds. So our function actually timed out before we got response. So in this case, our user-facing API returned a 502 to the caller. But if you look at the logs, the internal API actually eventually returned a 200. So from the internal API's perspective, everything was fine. So it turns out we had a mismatch or misalignment of our timeout values, where the caller function, the user-facing API function, had a shorter timeout than the internal API function that is calling. So this kind of timeout or misalignment can happen all over the place, because you may have many different user-facing functions all calling some internal API, and that internal API's Lambda function would have its own timeout based on what makes sense for itself. But whereas all of your other user-facing functions may not know what that timeout is. So it's very likely for you to have some mismatch, especially when different APIs and different microservices are run and managed by different teams. Beyond that, there's also potential mismatches there, whereby API Gateway itself has got a maximum integration timeout of 29 seconds. But your Lambda function can run for a whole 15 minutes. So it's very possible for you to have a Lambda function that can outlast the API Gateway invocation. Not to mention that there's also other things you got to think about as well when it comes to Lambda specifically, because it's the Lambda timeout only applies to the execution time for your function. If you have a function that has got really large dependencies that takes a long time to initialize, you may find that, well, on occasionally during a cold start, you may actually end up running for longer than your timeout should have allowed for, because you haven't factored into account how long that cold start for those functions are. So, for example, if you have, say, a function that's written in Java and using lots of heavy dependencies, then it's quite possible for you to have a cold start of a few seconds. So even if your expectation is that this function's timeout is configured to be 3 seconds, the actual response time that the caller can expect can be much longer than that 3 seconds, because you have to factor into account how long cold start itself takes as well. So turns out there's quite a few different things that can possibly go wrong, even in a very simple scenarios that we have here, where there are lots of different ways where those HTTP communication can go wrong. Not to mention the fact that if we just rely on some of the defaults from HTTP client libraries that we use, many of those will have default timeout of 60 seconds. So in terms of how do you set the timeouts correctly, how do you handle these kind of timeout scenarios, I've seen two main strategies. One is that you can divide your caller function's timeout equally across the different HTTP requests it has to make. So in this case, say our function has a timeout of 6 seconds, and it's making 3 different HTTP requests. So each request is going to get 2 seconds, but then some requests may get timed out, even though if you had just let it run, it had been fine, because we have enough time to execute all of them. The other strategy is whereby we take a more optimistic view of things, and every HTTP request gets the full 6 seconds. but then our function ended up timing out, even though none of the individual requests took too long, but together they took longer than the 6 seconds that we had. So our function timed out before we were able to finish everything everything we're doing, and so our caller gets a 502. So luckily for us, when it comes to Lambda, we can actually find out how much time is left in the current invocation using the context object. So I think a much better strategy here in terms of how do we handle HTTP requests we're making and handling dealing with timeouts is we can then set the HTTP timeout for every single request based on how much time is left in the current invocation. But we're going to reserve some time at the end so that we can do any kind of recovery steps like logging the timeout event itself, publish any custom metrics that, okay, we try to talk to this other service and we had a timeout. Or maybe we can fetch some cached response from previous requests, or maybe from some shared caching somewhere. That way, every request in this case is going to be given the best chance to succeed. And even when it fails, there's some time left for us to do some recovery. But if together, collectively, those requests did end up taking too long, and instead of just letting the function timeout and return a 502 to a caller, which is not a great user experience, we can then do something like fetching a previously cached response or return some default response instead. And to do that, you can see that we can add a few lines of code to our get restaurants function that we had earlier, whereby first we're going to use the context object. In this case, I moved into a global variable to check how much time is left in the current invocation, and then I'm going to reserve some time at the end. So I'm going to set a timeout for the HTTP request itself using the value that I have derived based on the amount of time that's left minus my reserve time for recovery. And then if the HTTP request succeeds, we can then take the response and then we're going to cache it somewhere. So that in cases where it does fail because we hit a timeout, then what we can do is let's just check. Do we have some previously cached response we can return? If so, great. Otherwise, do we have some default response that we have bundled into our application so that we can always return something? So returning this is useful, where returning something is better than returning nothing at all and just give a user a 502. The outcome, the result of doing some more extra work, I guess a few more lines of code, is that we end up with a system that is more resilient, which is exactly what we're hoping for here. There's, in terms of other errors that we can inject into our system, we can also say, let our functions throw an exception and see what does the system, how does the system handle it. This could be quite useful for background processing functions, whereby we want to check the retry behavior happens correctly, that we have the right DLQs and all of that set up, so that if there are some persistent errors happening with one of our, say, kinesis or SNS functions, that we're not just going to lose some events. And for API functions, so we can also just force it to return some HTTP status code. Again, very useful for testing API to API actions to make sure that we're handling the different possible scenarios here. Maybe sometimes we're missing some handling for fault 3, whereby we need to refresh our authentication token or something like that, whereby you are, or maybe we can fill up the disk, the temp directory, so that if there are function that relies on using the temp space to store some temporary data, then what happens if it runs out of space? Or in cases that we want to test what happens if you want to, say, talk to some other services and there's some networking issues happening, we can use the blacklist option from the failure Lambda library to simulate those as well. So this could be useful for testing, for example, what happens if there's something wrong with DynamoDB and that there's elevated the error rate from DynamoDB itself. So in this case, again, very simple setup with the API gateway, Lambda, turn to DynamoDB, and our function to fetch some restaurant from DynamoDB is, again, very simple. Just a one API operation against DynamoDB. And the hypothesis is that, well, something happens, then that's fine. The AWS CK has got built-in retry with exponential backoff and all of that. So everything should be handled just fine without us having to do anything. You run it, turns out it didn't work. And what actually happened was that my function, again, timed out after 6 seconds. So it turns out the DynamoDB client for JavaScript, at least, has a default of a maximum of 10 retries with an exponential backoff that starts at 50 milliseconds. And the delay between each retry is calculated using this formula, which Mark Brooker, who is a senior principal engineer at AWS, he professed at last reInvent that this is his favorite formula of all time. And so when you crunch the numbers, the max delay between retries alone can easily push you over, say, a 6-second timeout that you set for a Lambda function. And all you need for that is to get a couple of throttle exceptions in a row. So it's quite possible that the functions can get timed out because of this excessive amount of retries and exponential backoff. In fact, this happens quite often, probably more often than people realize. For example, quite a few people have talked about this already. I've also found this blog post from a seed last year, which talked about the exact same thing. And luckily, the sort of workaround here is just to override the default configuration and set something that's a bit more reasonable in terms of the max retry count for your function. And we can also add a fallback for reads as well, so that if we can't read the data from DynamoDB, then we can fall back to previously cached results or some static response. And for writes, we can also, instead of writing to DynamoDB straight away, and where DynamoDB is not accessible, we can also queue those writes up to say SQ, so that if something happens, at least we've got some background process that can retry those writes later. So hopefully, if the problem is temporary, then when the problem goes away, then our sort of retry process in the background, we just pick it up and then finish the write. So again, this is what I probably end up doing instead, whereby I will override the default so that I still have some retries, I still have the exponential backoff, but we're not going to retry for 10 times because my function has got a really low timeout value of only 6 seconds. And also, after the response comes back, we're also going to cache it as well, so that in the future, if something does happen, something does go wrong, then at least I can have some cache response that I can fall back to if that's applicable for the application. Or in this case, if that's not available, I can also return some default set of restaurants here as well. Again, the outcome is that we end up with a system that is more resilient to failures, which is exactly what we're looking for here. So those are just a few of the different type of errors that I can inject into my Lambda function using the failure Lambda library. But there's a lot more. So those are just some of the application failures that I can test to make sure that my application can handle different failures correctly. There's a lot more you can do, including testing how your application handles spikes in traffic, or maybe different size of payloads. If you've got, for example, you are writing those files to disk, or you are loading them into memory, and your function is configured with 128 meg of memory, but then someone uploads a really large file to S3, triggers a Lambda function, and then your function runs out of memory. So basically, anything that can possibly go wrong in your application, you should be thinking about that as a potential scenario and test them to see how your application actually handles them, and then react accordingly. Because again, everything fails all the time, and you don't have to, and you shouldn't stop at your application layer either. Try and apply chaos engineering practices to your processes as well, and make sure your procedures are both effective and that everyone is familiar with them, and everything is well drilled to make sure that when problems do happen, they are identified quickly and rectified quickly. And as much as possible, your application should be self-healing so that it will just deal with those problems without requiring downtime. And that brings me to the end of this talk. I want to thank you guys again for being with us this evening. And also starting, if you want to learn more about how to build production-grade serverless applications, I'm running an online course in a few months' time. So go to this link to check it out. And as I mentioned earlier, I'm also spending most of my time as an independent consultant. So if you want to see how serverless can help your organization, or how you go faster, then see how we can work together, then go to my blog, theburningman.com, to see how we can, the different services that I offer. And again, thank you so much, and hope you guys stay safe wherever you are.
Well, thank you very much, Yan. It was very interesting. For the moment, I don't see any question coming from YouTube or Twitch. Maybe we can wait for a few seconds more. If you have any question, you can ask it directly on the chat of YouTube and Twitch. And Yan will probably stay a little bit longer to answer the question you may have. So feel free to ask him any question directly on the chat. Well, thank you very much, Yan. We'll go to our third speaker. I'm just sharing once again my slide. Thank you, Yan. Thank you for coming. So the third speaker of today will be Gunnar. Gunnar, are you with us?
I hope so.
Hey, yeah, I hear you very well. How are you?
That's good. I'm good, thanks.
Perfect.
Very well.
So Gunnar, you have 20 minutes. You can start whenever you want and see you at the end of your talk.
All right, thank you. Hi, everyone. I am Gunnar Grosch, and really great to be here with you. Just finished up a talk short while ago in Lebanon, and now off to Paris to do this. So great. And we're going to talk about verification of serverless applications. And verification, let's just say that it's an add-on. We're going to use chaos engineering for it. So let's jump into it straight away. The agenda, quite short. First off, a few words around serverless before we jump into a few words around chaos engineering, and then move on to from chaos to verification, and hopefully in the end do a few demos on it as well. So shortly about me, I'm an evangelist working at Opsio based in Sweden. I'll be there for at least 3 months more now, then off to new adventures. My background is, well, figured out earlier today that I've been in IT for 20 years now. So I've been in development, operations, and management. I am an organizer of user groups and meetups in the Nordics. Also help out organize conferences like the AWS Community Days and Serverless Days as well. I am an AWS Serverless Hero. Glad to be honored with that badge. I'm also a father of 3 kids. So when I'm not in tech, well, I'm at home with my kids most of the time. All right, so let's get to it. Most of you probably know all about serverless already, so I just want to look at a few things about it for context. So this is the AWS definition of serverless, and it states that serverless allows you to build and run applications and services without thinking about servers. And the without thinking about servers part is the main one. And this is not so much about the actual servers as it is about what running servers means. It's about letting someone else do the long time work that is involved with running servers and lets you focus on maximum business value. So we don't have any server management. There's no servers to provision or maintain. There's no software for us or any runtimes to install, maintain, or administer. Our applications have flexible scaling in that they can be scaled automatically from 0 to the highest peaks or by adjusting capacity units rather than the number of individual servers. And we pay for consistent throughput or execution duration rather than, once again, the number of servers, the server units. And serverless provides built-in availability and fault tolerance. So you don't need to specifically architect for these capabilities on the service level, since the services running the application provide them by default. But it's important to remember, and I think Jan's talk showed that quite detailed, that there are still a lot of things for us to think about around serverless to build them reliable and to get that resilience. So if you ever talked serverless with an old server hugger, you've probably heard this line that there are still servers in serverless. And Yes, there are, but we just don't manage them. So this leads us to some of the challenges as well with serverless. So we don't have any servers to manage, and that also means that we have potential sources of failure that we don't or can't control. So the failure modes for the underlying infrastructure is quite unknown for us. And I'm all for less infrastructure work. We just have to remember that every time someone setups or configures infrastructure, they usually learn a lot about how it works, and they find potential sources of failure and are aware of them. So once again, in serverless, things are unknown for us. And the serverless landscape today has lots and lots of services for us to choose from. Besides serverless functions, lambdas, as perhaps the most common part of our architectures, we have a vast amount of services to choose from. We have S3, SQS, SNS, EventBridge, DynamoDB, and so on. And each of these have their own potential sources of failure and unknown failure modes. And for each function and each service that we use, we have separate configuration and we have separate security policies. And this is great for control, but it also gives us the opportunity to introduce failure into our application. And also that our serverless architectures are usually more granular in that they contain lots of functions and lots of services and the interconnections between those. So all in all, we have more inherent chaos in serverless. Chaos engineering is, for me, a perfect fit for serverless. And what I mean by this is that with the inherent chaos and the granular architectures, serverless is well suited to use chaos engineering with. So we can use chaos experiments to help build more reliable and resilient applications, and basically with just the AWS CLI to get started. Serverless applications are distributed systems by default, so using chaos engineering can help us verify that things work as intended. So that's easy for me to say since I've done a lot of chaos engineering. You've heard 2 talks on it already, so I'm not going to deep dive into this specific topic, but a few things around chaos engineering. Chaos engineering is about finding the weaknesses in a system and fixing them before they break. So no matter how much we focus on making our systems resilient to failure, there are always unknown factors that come into play. It can be traffic patterns, third-party dependencies, network issues, code deploys, configuration changes, and so on. So by doing our experiments and measuring the result, we can draw out weak points in the system. And finding these and fixing them can help us avoid that big outage. And we know that big outages rarely happens at the right time. And chaos engineering is about building confidence in your system and in your organization. Patrick talked about this. By finding weaknesses and doing controlled experiments, we can build confidence in our system and how it works. But as important is that we build confidence in our organization. People are key when we want to build a resilient system. And by building confidence in the organization, we gain trust. So perform chaos experiments and you'll learn new things about your application and most likely also about your organization. And this brings us to the, for me, greatest motivation behind chaos engineering. Don't ask what happens if a system fails, ask what happens when it fails. A resilient system isn't one that doesn't fail, but one that maintains an acceptable level of service in this phase of failure. So what happens when the system fails? Well, chaos engineering helps us reveal that. So using chaos engineering to find weaknesses in a system is great. Building confidence in your system and your organization is great. I think everyone agrees on that. So why aren't all companies using chaos engineering? Well, first of all, it's the name. Patrick touched on that as well, that chaos engineering, the chaos part sounds like we're going to do chaos on our system. But also it can be complex. It is a risk of using chaos engineering. It's an extra thing to care about. It might drive cost and so on. So that brings us to the term of verification. And we have all of this complexity in our systems today. So how do we move fast and not break things? And verification is a proactive experimentation for verifying system behaviors. So we as an industry, we're usually good at reactive measures like incident response, disaster recovery, and testing methods like unit tests and integration tests. But verification is a proactive experimentation for verifying system behaviors. And verification tells you why it's important to explore a set of conditions. And the impact on something that you care about in your system. So let's dive into that. Verification consists of a few parts. First off, we have the objectives. And the objective is something that you care about and which shows that your system is available. Page loads, clicks per second, processing speed, etc. And the objective might be defined at the business level. For instance, I want 200 clicks per second. Or it might be on a technical level and tied to service. My purchase API should respond in less than 400 milliseconds. Those are two examples of objectives, things that we care about. And the objective must, of course, be measurable. So we might, for instance, track the number of clicks per second and add 200 as a threshold, and then we measure the purchase API and add the latency threshold we defined earlier, that it should respond within 400 milliseconds. So that's the measures part of our verification. And then we have the what we call conditions. And conditions reflect an event that could occur in your system. So this is where the chaos part, chaos engineering experiments come into verification. So we can now add our chaos experiments as a condition to our system verification. What if we add an additional 100 or 200 millisecond latency to each API call? Will the API still respond in less than 400 milliseconds? What if there is a downstream service error? Will we still get 200 clicks per second? So with the objective, the measures, and one or several conditions in place, we can then verify our system behavior. And so we use the conditions that we added and we verify, do we still have an API that responds in less than 400 milliseconds? And for a site reliability engineer, this might mean that the objectives are the SLOs and the measures are our SLIs. And the condition, of course, is an event that might occur, something that we, by using chaos experiments, add to our verification. And that moves us to quite new concept of continuous verification. So this is part of an evolution that we're seeing from CI with continuous integration, which kind of limited the number of bugs that we can create by merging code faster, so bugs become more apparent and don't perhaps lead to a larger number of bugs. So engineers can create features faster. And now we can create software faster. That evolved into continuous delivery, CD. So now we can get it to production faster and roll forward faster. So the next step from that then is to do the verification we just looked at, but in a continuous way. And that is CV, continuous verification. So we're doing our verification, but in a continuous fashion as part of a CV pipeline. And there are today 2 tools available for continuous verification. I don't work for any of them, but I'm a fan of their work. We have Chaos IQ. They also run the open source Chaos toolkit that can be used for chaos engineering experiments. Russ Miles is one of the persons behind that. And then we have Verica with Casey Rosenthal and Aaron Reinhardt and a few other legends in the field of chaos engineering running that company. And none of these tools so far support serverless workloads for continuous verification, but hopefully that will be added soon. But both are tools that will help you to use continuous verification. So let's look at how we can use that then in a serverless conditions demo. And I've created a simple website that can be used for doing chaos experiments on a serverless application, and it's really simple. It's nothing advanced, but it's there to help people get started doing these types of experiments. And so we're able to add these chaos experiments as conditions in our verification. And so we're going to use that for the simple demo now. This is the architecture of it. It's a simple web service where the client is getting static data from an S3 bucket. We have an API gateway in front of 3 different Lambda functions. We're using 3 in this case to be able to show off 3 different experiments. And the Lambda functions are fetching data from a downstream service, DynamoDB, and then returning that to the client through the API gateway. And we'll be using the failure Lambda NPM package that Yan talked about. What he failed to mention is that it's more or less entirely based on a blog post he wrote in, I think, 2017. So even though it's published under not my name, it's more or less Jan's work, all of it. And we're using this package on our Lambda functions, and we are able to control it using parameter store. So in the parameter store, we have simple JSON that says if it's enabled or not, what failure mode we're going to use, and so on. And the different failure modes, Jan went through them excellently, so no need to do that again. And moving on then to the actual experiment. So we have this architecture. And what if my function takes an extra 400 milliseconds for each invocation? What if my function returns an error code instead of a 200? What if I can't get data from DynamoDB? So those are the what ifs and that we base our hypothesis on. And the hypothesis in this case might be, well, if we inject failure to our lambdas, the application will gracefully degrade. But let's try it out to see how that works. So switching over to, this is the site. So we have the 3 Lambda functions, function 1, 2, and 3. They're loading right now, giving a 200 response, all of them, and about 200 milliseconds invocation time. For each invocation, it's fetching data from DynamoDB. It is returning an URL for a new image and then loading that image on the client side. All right, so these are all prepared, so they have the package installed and ready. Oops, switching again. So these are the 3 functions. Let's just open function 1 to quickly show you. All right, so we have the package, and then the handler is wrapped with the failure Lambda package. So by that, we are then able to inject failure, and we're doing that with the help of parameter store. And this one is tied to this specific parameter. So let's move over to parameter store. Here we go. As I said, it's basic JSON. Right now, it's set to false, so it's not enabled. The failure mode on function 1 is set to latency. with a rate of 1, which means that it will inject latency on all invocations. It has a minimum latency of 100 and a maximum latency of 400. So let's just enable that and see how that works. Change it to true. Going back to our demo site. So looking now at function 1, we can see that right now it's showing more or less the same, but it is for each invocation adding an additional 100 to 400 milliseconds. So the latency for that function is a bit longer. Still working, it just takes a bit longer for each. So we can then adjust that and add additional latency if we want to test other things as well. So let's do one more just to see that. Let's take failure lambda parameter number 2. Also set to false right now with the failure mode set to status code. I have a rate of 0.5, which means that it will inject failure on about half of the invocations. I've set the status code that it will inject to 404. So instead of returning a 200, it will return a 404. So let's edit that one. I'm doing all of this through the console right now, but this could, of course, be done using the CLI instead to make it even faster. There we go. Yeah, and as soon as I switched, we can see that it's instead returning a 404 now for this invocation. And as I said, we had a rate of 0.5. So on the next one, it was a 200. Then it's a 404 again. And this gives us the option to test certain conditions, how we're handling these errors on the client side in this case. And let's do the last one as well, just for fun. So number 3, set to false right now. The failure mode set to blacklist. And blacklist, as Yan explained, it means that we're able to intercept network calls and then block those. In this case, the blacklist we have is calls to S3 and calls to DynamoDB. And in this case, DynamoDB will be affected then. So let's enable that one. There we go. And now, for the next invocation, as we can see, instead of 200 and loading a new image, we're getting a 502. And this is not a 502 that we're injecting as with function 2. Instead, this is Lambda having an error and API gateway returning a 502 for us. And we're not getting a new image because the Lambda function is unable to retrieve data from DynamoDB in this case. And using DynamoDB, well, that's one example, but it might be any type of downstream service or third party, for instance. If we're using a third party for something, we can block those as well to see how do we handle a service interruption for a third party. So this is a simple way of doing these experiments. And the next step, of course, then would be to learn from it, see how we could improve the application as Yan showed before, but also on the front end side. How do we handle these errors in our user interface using graceful degradation and so on? All right, so back to the slides. Next, I want to show you another way of doing this. By using another even easier architecture. This time we only have one Lambda function with DynamoDB as a backend. Because what we did right now would mean that adding latency or blacklisting or something like that in the way we just did, that would mean that all users would be affected by it. And that's perhaps not the best way to do these experiments or to do our verification, because we want to have a small blast radius, and that blast radius is as big as it gets. So another way of doing that might be to use canaries. So sorry, let me just close the window. There we go. So we can use canary deploys as a way of controlling how big part of our lambdas should be affected by these failure injections. So we could use, for instance, 10% of lambdas, deploy using canaries, and enable that failure mode on those 10%, which would then make a smaller blast radius, which we would then make it possible for us to control or verify a smaller subset of users, for instance. But there are issues with that as well, because let me show you quickly. There we go. So I've made a simple site for that as well, that perhaps acts like a bigger number of users. In this case, we have 12 different users calling that specific lambda shortly. On next invocation, all should be 200. There we go. And then we could use canary for this. Let me show you. So this application is deployed using serverless framework, and I'm using a plugin called serverless plugin canary deployment, which does just canary deployments. So I have one single Lambda function being used by all of these mock users. I've set the deployment setting to canary and 10% in 5 minutes. So for the first 5 minutes, only 10% will get the new version of this Lambda. I have two different parameters now. One that is disabled, which doesn't inject failure, and I have one that is enabled, and that, of course, then injects failure. I've set the failure mode to status code in this case. And if I just change this to the enabled one instead, and then deploy it, this should kick off a canary deploy, which takes a short while because it's using code deploy in the background. So what it will do now is it will give us a canary deploy so that 10% of users will use the new one with the failure injection. And that's a better way to then control how many users will get this failure injected. So this takes a while, so we can just go on to look at the next example during that time. And the next one is another way of doing it. Still have the same architecture, but instead of using a canary deploy for the Lambda, we can use for instance, feature flags. So we're using different version APIs, and then by using feature flags, we can control which users get the new version API, which then leads to the Lambda function that has the failure injection enabled. And in this case, one user out of 12 will get that new version, while the other ones will get the disabled version. And that gives us another way of controlling it. Then we have to control it on the front end, of course, but then we can control exactly which users are getting failure injection and not. So let's see. All right, so this is the site now with the 12 users. And now we should get about 10% of them should get a status code 502, as we can see. But this also shows us the problem with using canary deploys for Lambdas, because based on how our application works, well, it will inject error on 10% of invocations, but we don't know which 10%. So in this case, the blast radius is still as big. Because all 12 users might get the failure injected Lambda, since we aren't able to control which user gets it. So in that perspective, well, perhaps API versioning is a better way, using some front-end logic with feature flags or something like that. All right. So if you want more about this, it was all quite brief. Here's some links. Follow Serverless Chaos Twitter bot, retweets around chaos engineering, link to the chaos demo app, to all of the different failure packages. Besides one for Lambda, there's one for Azure functions and cloud functions as well. Adrian Hornsby has a Chaos Lambda package for Python. There's a Serverless Chaos Lab by Jason Bartow. I have some more videos and repositories on my site as well. And with that, I guess, any questions?
Yes, thank you very much, Gunnar. The first one is concerning your last demo. It's coming from YouTube. And the question was, are these synchronous Lambda or asynchronous?
Well, these are all called through API gateway. So what's the second part of the?
The second part of the question is, does this change the results of the failure?
No, I don't think it should. When we have the blacklist one, for instance, it will do retries for DynamoDB. So I guess that's it affects that. So it's a way of testing the retries as well. So using, for instance, the rate limit or the rate in if we set the rate to something else than 1, it might be in that the second or third attempt will get through. So that's a way of using that.
Okay. Another question is coming from Twitch. How does verification differ from testing?
Yeah. Well, let's say that it's really related to testing, but verification is more based on the deployed system, the system that is in production. So it is verifying the system, but under production-like conditions, and while adding additional conditions like the chaos experiment. So it differs perhaps in the way that this is more proactive than reactive, because testing would fall under more of a reactive way of you're testing certain conditions, while this is more of a proactive approach.
All right. Well, to finish, we will have a last question from Yan asking, what do you have on your cap?
Yeah, because my hair looks like this, I guess. So yeah, that was the short answer.
Well, thank you very much, Gunnar. I hope you will stay a few minutes long for answering some other question that can come to the chat. Thank you very much for coming. And now we'll go through the agenda with our last and final speaker. We are very proud to have you here. How are you, Adrian?
I'm fine, thank you. You hear me all right?
Yeah, very good. Thank you for coming to the French AWS user groups meetup.
No problem.
I leave you the stage. You have as many time as you want. And thank you once again for being here today with us.
Okay, can you see my slides?
It's working. Yeah. It's good.
That's all working fine? Okay. First of all, I'd like to say that I told my wife I was doing a talk to a user group in Paris in France, and she said she was very sad because she wants to go visit Paris again. So sorry that we can't be there in person right now, but looking forward to visit again sometime soon. So this talk is it's the same slides that we used for a talk at reInvent. You can see the reInvent code there for 2019, ARC 335. I'm only going to present the section that I gave. there were actually 3 parts to this talk. One part by Harsha went through the AWS products and how to configure them. There was a customer section talking by Snap, the Snapchat people, talking about some examples of how they use multi-region high availability. And then the final section was the part that I'm going to give on continuous resilience. Now, when they recorded the event, at reInvent, it was recorded twice. I presented the first time and there were technical issues. So if you go find this video, it doesn't have me giving these slides. It actually has Pawan and Igotri giving my slides. So this is the same slides, but I get to give it instead of Pawan. So hopefully that's novel enough for people that might have already watched this talk. So I'm going to talk about continuous resilience. There's something Gunnar brought up recently, continuous verification. What we're really doing here is taking some of the ideas that we've brought through from continuous delivery and continuous development and saying, instead of having resilience be something you test once a year or very infrequently, that it's something that you are continuously proving that you have the resilience that you think you had. And what's really motivating this is data center to cloud migrations, which are not just for, say, new applications, but people are closing their entire data centers. This means the business and safety critical workloads are starting to move to cloud over the, well, not starting, but over the last few years, we've seen several customers move their back-end systems. And so what we're developing is the patterns, solutions, and improved AWS services for customers, but particularly in travel, finance, healthcare, manufacturing, where the more traditional workloads have tended to be the ones which were the last ones to move out of the data center. And historically, what happened from the 1970s onwards is that people had disaster recovery sites. They'd have a separate building or a separate data center, and they'd have a failover plan in case something happened to their primary building. What we have in the last 5-10 years is we've been talking about chaos engineering, mostly in the organizations which we tend to call scaled digital native organizations. Netflix obviously is one example, but many of the more cloud-based organizations adopted chaos engineering, partly because the automation that cloud provides is also the automation you need to do effective chaos engineering. I think this explains why chaos engineering started to happen at the same time as cloud, and it didn't happen in the same way in data centers. What we want to get to in the future is continuous resilience, which is like, instead of having chaos engineering being an infrequent thing, make it something that happens all the time. So if we've had a few customers say they don't like chaos, they don't want chaos in production. So if we change the name from chaos engineering to continuous resilience, will you let us do it all the time in production? And there's a few people that have said, yeah, sure, I really do like the idea that I should have continuous resilience in production. I want that, but I don't want chaos engineering in production. And it's the same thing. We're not talking about doing anything different. Sometimes the name matters. So if you run into that pushback and somebody says, I don't want any more chaos, just say, would you like continuous resilience instead? So it's more marketing than anything else, but sometimes the names matter. I did a blog post last October or so on failure modes and continuous resilience. You can find it on my Medium account, and I go into some detail there. I'm working on more blog posts in this area. So the point here is that you can only be as strong as your weakest link. This is the problem with resilience. And the thing that breaks is always going to be the weakest link. It doesn't matter how much work you've done on all the other links in your chain. You'll miss one, and that will be the weakness. You need to have a dedicated team to find those weaknesses. And if you think about it, availability, safety, and security do have similar characteristics. It's very hard to measure a near miss where the system didn't fail, nobody got hurt, and there wasn't a break-in. But you came close because, right? So that's a difficult thing. You should figure out a way to measure those near misses. They're also based on very complex dependencies, which are hard to model. And they all have catastrophic failure modes, right? Everything's fine, and then all of a sudden your site's down, somebody's hurt, or there's a break-in. But they also have similar mitigations. We tend to have layered defense in depth. We have safety systems for availability. We have a failover place to go. We have safety catches and backup systems for industrial safety and human safety. And we have layers of security. So if someone breaks through one layer, there's another layer behind it. You know, you've not only got a firewall, you've got encryption, and you've got network isolation, all of those things. We have bulkheads to contain the blast radius. And that means that when you have a failure, your entire system doesn't go down and or cause a problem. It's a contained problem. And they also depend upon minimized privilege or minimizing the dependencies and knowing what those dependencies are. So you can understand what locally is going to break and what touches that and how to manage those resilience across those boundaries. But they also break each other. A large number of availability failures are caused by security breaking, like a certificate timing out or a denial of service attack that takes out the ability of the security system to figure out what's going on, and then it blocks all of the other traffic. Sometimes availability can break safety, meaning that in order to keep a system running, you're actually running it in an unsafe mode when you should have stopped it. So there's interactions between each of these. So we have to think a bit more carefully, particularly as we start thinking beyond availability and security, and we're looking at safety critical industries. I talk to mining companies, and the trucks that drive around the mines don't have a driver. They are self-driving vehicles. They're huge. The wheels are 20 feet tall. They have covered with LiDAR sensors, and they drive, and the roads that they drive on change every single day because it's in a mine and the roads move. There isn't a fixed road. So some really interesting challenges and a lot of automation. The software that operates them has to be safe, right? So what should your system do when something fails? One of the options is stop. And this is, quite a common situation. If you're writing some code and it says the world all of a sudden gives you an error, something happens, you get an error, maybe you throw an exception, you just stop processing. Another option is to say, well, I have a fallback. If I can't get this data, I can continue with some kind of reduced functionality. Maybe part of the website shuts down, but the rest of the website continues to work. However, because it's really hard to test all of the failure modes, what often happens is that you start executing some failure handling code, and that's not well tested, and it crashes the whole system. So this is another problem you tend to see. You see systems that are running fine, and then a small problem happens, and that problem triggers the system to have basically a complete collapse. It will spread and spread until the whole system isn't working. So for example, if you just get a permissions lookup, you're executing the code, you have a customer ID, you try to look up that customer to see if they're a valid customer, and that fails. Should you stop or should you continue? Well, this is context dependent, because what you probably want to do if you're optimizing for availability is have a permissive failure and continue as much as you can. What it comes down to is, what is the cost of continuing? There's a good book called Memories, Guesses, and Apologies by Pat Helland, a good paper, which talks a bit about The apology piece is how you manage it when things go wrong. Sometimes the best thing to do is print a phone number on the console and say, call customer service. They'll sort it out. And that can be one of the most reliable ways of handling things that break. But you also want to think about the difference between showing somebody a movie and you're not sure if they're still a valid customer. At Netflix, where showing them a movie is such a cheap operation, you should just let them watch it if you're not sure if they're a customer, because their cookie might have timed out, but probably hasn't. But if you're in finance and you're moving $1 billion from one bank to another and the permissions lookup fails, you should stop. And you should wait until it's safe to continue, because the cost of getting that wrong is much higher. So this is a question I like to ask CIOs and architects in the customers I speak to. Do you have a backup data center? And they say, yes, normally, yeah, we have a backup data center. And then I ask, how often do you fail apps to it? And they say, well, either never, or we're going to do it one day, or if they're in finance or a regulated industry, it's usually once a year is the answer, because the auditor comes and makes them do it. And if the auditor didn't come, they wouldn't do it once a year. How often do you fail over the whole data center at once? Have someone go in there and hit the power switch on a data center, or cut the network link? And really, almost nobody does this. I found 1 or 2 instances, but it's incredibly rare. So I call this availability theater, because people went through the motions of setting up a backup data center and a recovery plan for business continuity, but they don't really test it often enough for it to work in practice. It's a little like what they call security theater, where you're going through the motions to be secure, but you're not really secure. So we have this fairy tale that once upon a time, in theory, if everything works perfectly, we have a plan to survive the disasters that we thought of in advance. It's not a good fairy tale. It'll keep you up at night. Not a good bedtime story. Here's a few cases. Think about the company you work for, and you probably have a web presence on a domain. Think if that domain name went offline. Somebody forgot to renew it. Now, nothing with that domain works. This happened to a SaaS vendor, one of the big SaaS vendors. All of their product was on that domain, so was all of their internal email. So they couldn't communicate, they couldn't log into anything, they couldn't reset anything. The entire company depended upon that domain name working. So all they had was a Twitter handle and the CEO apologizing on Twitter for about 2 days before they managed to get everything working again. So think about what that would look like for your company, and maybe it's a good idea to put your email on a different domain than your primary product if you're a SaaS vendor. Maybe it's good to have a backup DNS provider and a way of failing over, or even backup domains that your application could switch between if there's a problem with one domain. There have been occasionally denial of service attacks against DNS, which have caused difficulties. And even, do you really need DNS? If you're talking to an instance which is going to be at a fixed IP address, then you don't need to look up the IP address to talk to it. So maybe your internal traffic, you can resolve it at the time the system is created, an instance is started in the cloud, and just talk directly to the IP address. And that's, in some cases, used to make systems a little more robust. This has happened to everybody. Security certificates have a timeout. They time out, things stop working. It happened at Netflix. It's happened to just about everybody. We put a lot of effort at AWS into registering applications and their certificates. We make sure we don't renew all our certificates at the same time. We don't issue them. So we don't have a cluster of certificates timing out at the same point in time. We spread them out and we track them. And we still occasionally have maybe a new service comes up and somewhere in the code base there was a certificate that somebody didn't overlooked. We still occasionally get glitches because of this, but this is something that takes a lot of diligence. I have a good friend who was working for a finance company in the New York area. They had a data center in a basement in Jersey City, and it flooded. And that's when he discovered, well, that's when everybody realized computers don't work underwater, and they don't work when they're full of sand and bits of seaweed and stuff, and dead fish when the water's gone away. And so they started moving data centers to higher floors. We also discovered, other customers discovered that you shouldn't put the generators in the basement. And some different customers discovered you shouldn't put your fuel tanks for your generators in the basement. And your network cabling for some of the large internetworking sections of Manhattan were in a basement that was flooded. And there was some physical paper documents, which, that were, archives that were in the basement. They had to go dry out, a lot of documentation. So basements aren't really good if you're anywhere near the sea. Hopefully this doesn't happen to you anytime soon. So there's a few good books I want to recommend, and this is one of the most fundamental ones. This is something I found about a decade ago. I shared it around everybody at Netflix. A lot of people read it, because what we found was that we'd got pretty good at defending against the known knowns, the failures that we could see happening. What happened was the failures we were getting, the remaining failures, were always new ones. They'd never been seen before. They were strange, bizarre combinations. They were like, these 5 things all went wrong at once. That caused the failure. And they were things which snuck up on us, where the system was working fine, and we gradually ran out of capacity to absorb that last thing that would tip it over the edge. So this book talks a lot about aircraft crashing and people dying in hospital, but it's a very good book to get your head around the need to capture and learn from near misses. The safety we have in the air industry is largely because every near miss is logged centrally. It's captured, it's logged. If anything is even remotely wrong with a plane, it's shared by every airline that looks after that type of plane, shares that information. So there's a huge system for tracking this to make air traffic safe. We need that kind of thing for making computer systems safe. So when I think about chaos engineering, I like to divide it into a few different areas. The infrastructure area, the switching, the tools used for switching between different pieces of infrastructure, the application itself, and the people. And a chaos engineering team is using tools to try and test all of these layers, try to find the weak link. You run game days to prove that people know what to do. You do module testing on applications. You feed them bad data and latencies and things like that to show that they're robust. You practice switching between alternatives, backup data centers, backup regions, backup zones. And you have redundant infrastructure, and you know how that behaves. It's also very similar to the security red team approach, where there's a team trying to do penetration testing, trying to send spoof emails to people to spearfish them, or to sort of activate people's alerting for the kind of patterns to look for in those emails. A similar kind of idea. So to get this defense, what you need is experienced staff that have done game days. They know what it looks like. They know how to access the tooling they need to manage an outage, and they know how to how to log in, how to work together, and how to coordinate around, say, a conference call or a Slack channel that is being used to manage the failure. You need robust applications. You need a dependable switching fabric, and you need redundancy in your foundation. One of the interesting things here is, since you can't predict everything that might go wrong, the best thing you can do, the most general thing you can do, is get very good at fast detection and response. Chris Pinkham was the original engineering manager for EC2. He said this once in a joint talk we were giving about a decade ago, and I wrote it down, have used this ever since. It's a really good way of thinking about it. I've been most recently thinking about a more rigorous approach to hazard analysis. In particular, this book, Engineering a Safer World by Nancy Leveson. This is a team at MIT. They work particularly in aerospace. This team worked on validating the software that's used for air traffic control and for nuclear missile launch systems. So they've worked on some big, hard problems. They've come up with some good methods. So I'm going to show you what these methods look like, or at least this is a very distilled view of part of what they talk about. Here's a model. There's a control process at the bottom. There's some kind of automation controlling it, and there's a human watching that automation. I'm going to change some of the names here to give you something that looks more like a software system. Let's say there's a financial services application. That's what we'd call the data plane. Customers are making requests against it, whether via website or API calls or whatever. And once the application has accumulated all the right information from the customer and validated it, it then says this is a completed action and sends that on, right? Fairly straightforward. So that financial services app could be a microservice of some kind. It's obviously got disturbances coming in for various types. There's a control plane. Think of that as an autoscale group, either an EC2 autoscale group or a Kubernetes autoscale group or something like that, that is controlling the number of instances of that financial services app. And then you've got the human watching over the system, looking at some charts, getting alerts, who's watching the throughput to make sure that the app is processing and is continuing to process. So if completed actions goes to 0 or drops suddenly, you would get an alert at the human controller level, and they'd have to think about what to do about it. Many of our systems that we work on can be divided into these 3 layers. But the problem is we tend to combine together the control plane and the data plane logic rather than separate it cleanly. We tend to not think too hard about the human controller piece. So that's the human experience or the user experience, the controllability of the system. So what can go wrong? If we're looking at what could the human be doing wrong in the system, they could be looking at a system. Let's say we see a sudden drop in throughput. Completed actions has dropped. What's the human going to do? They could not notice, not provide any action. They could do something unsafe. They could do a safe thing, but actually, provide too early, right? Maybe it was just a glitch and the system's actually going to be completing anyway, so they overreacted. Or they could react too late. They could do things in the wrong order. They could start fixing something and then decide to, give up whatever they were trying to do. Or they could continue for too long. Maybe things like, this is the kind of thing like rebooting the machine is something that people tend to do. We can have coordination problems where there are multiple human controllers who aren't talking to each other, that all see the problem, and one decides to reboot the system, the other one decides to change the autoscaler, that kind of problem. And also, we get degradation over time. The written procedures, the run book, is probably out of date because it reflects the system as it was originally built, not as it's currently running. So these are general hazards. And when you think about human controllers, you can go down this list and think, what can you think of examples in each of these different types of hazards? If we look at another part of this diagram, and notice I'm not focusing on the boxes, the app itself or the control system or the human. I'm looking at the interfaces. When we look at hazards, We look at the wires in the diagram, not the boxes. We look at the information flow that is going on, or the control flow that is moving between systems. So in this case, maybe the app stops updating the sensors. So the system was working fine. You just saw 0 throughput because it stopped updating the dashboard. Or maybe it just zeroed out for some reason, or the numbers overflowed and went backwards for a bit. Maybe some data got corrupted, or some data get delayed in the system and you're getting data out of order. Data can come out too fast and overload your sensor system or your monitoring system, or just be too infrequent so you can't see what's going on because you get data once every 5 minutes and the problem is happening in seconds. Again, coordination problems, degradation over time. System was working fine, but your sensor monitor has a memory leak or a garbage collection problem and it degrades over time. So again, you can look at all of the types of sensors that you've got flowing in your system and look at these kinds of hazards. The third kind of hazard to think about is the models. The human has a model of the behavior of the system, which they get through training and experience. And one of the examples here was the Boeing MAX 8, where the pilots were not trained in the new control system that was doing anti-stall operations on the plane. And the planes started behaving in a way that confused the pilots, and then some of the planes crashed. So this is a problem in the model of automation due to lack of training, or where the control plane behavior changed in the system. So that's a model mismatch. You can be looking at throughput or looking at CPU capacity when the system's out of memory, so maybe you're looking at the wrong thing. And again, similar kinds of questions around updates and coordination problems. So if you think about the control side, the sensor side, and the models in the system, you can go through a design and figure out where the weaknesses are using this hazard analysis. And if you want more detail, you can read the book. But this is my current favorite way of analyzing something to try and harden it. So as I mentioned before, I think cloud provides the automation that leads to chaos engineering. But there's some good resilience practices for cloud. So I'm going to talk about a few of them. One of them is the rule of 3. It's good to have failover, but it's good to have 2 places to failover to. It's often better to have 3 ways to succeed. So if you're copying data, if you're storing data in a region, you want to store it in 3 zones in a region. That gives you the ability, if there's corruption, to look at all 3 copies and say the 2 that are the same are the ones that are likely to be right, and the one that's different is the one that's wrong, because occasionally you can get stale or corrupted data. So that's one reason for using 3 copies. But also, it gives you the ability, it helps bound the latency, because if you're running in one zone and you're copying the data to 2 other zones, as soon as one of the other zones completes, you're safe to carry on. So what that means is if there's a garbage collection or a network glitch in one zone, it's not going to delay you. So if you're trying to do bounded latency, your 99th percentile long tail latency is too long, having 2 places, 2 ways to succeed is a way to collapse that latency down and make it much more stable, because the long tails will only happen in one side or the other. So that's a very powerful technique as well. If you're doing DR failover, one of the ways of doing this is to go from a primary region to either of 2 secondary regions. And if you're looking at systems that need extreme availability and are very high value in terms of their workloads. But that's for failover, but also active, active, active is commonly used in 3 regions, because you don't need to have double the capacity. You just need 50% extra capacity, because you'll be going from dividing the work by 3 to dividing the work by 2. And that's a less peak growth in the capacity needed. Another thing to think about is fail up. So if you're running in one of the biggest regions and you're failing over to a smaller region, then you might find that when you fail over, that there isn't enough capacity in the smaller region for you. Now, as AWS gets bigger, and this is really only an issue for the very largest customers of AWS. So most people, this doesn't really matter, but it's still something to think about. And if you're worried about it, you should be running normally in one of the smaller regions, and you should use the larger capacity region as your failover region. So you might want to run in, say, the Paris region, which is a relatively smaller region compared to Dublin, which has been around much longer and is one of the larger regions in Europe, right? So run your primary in Paris, but handle failover to Dublin in case something goes wrong. The other thing is you might want to run, if you're worried about latency sensitivity, you might want to run most of the time in a region that's further away. And when you fail over to a region that's physically closer to you from a latency point of view. So in this case, you'd probably want to run mostly in Dublin and then fail over to Paris if you have latency sensitivity. The problem you're avoiding here is that if the system may not work if it's having to go further away, you may get timeouts if your system is used to short latency or in the system. Another core principle is chaos first. So you should build your resilience environment with automated zone and region failover testing and attacks on individual instances like chaos monkeys and latency and failure injection. You should have that set up as a test environment, put an application in it, and have a sort of a badge of honor if it passes that test to say this application has survived all the chaos testing, and that's a gate for getting it to production. And then another app that fails, you send it back for more remedial work before it's allowed to go to production. Done right, this can create a strong incentive from management to say, you have to pass the chaos test to be a really solid production system. So continuous delivery, if we think about that, the way that's done needs test-driven development and canaries. So use test-driven development to make sure that the new version of your system, your microservice is working. And then you do canary testing to prove that it works in production. It's a very similar model for continuous resilience. You need automation in the testing and production side. This is not something that you're going to be doing with a manual operation. So what we do here is we make failure mitigation into a well-tested code path and a well-tested process. And you can call it chaos engineering, but I think it's a little different here because what we're looking at is continuous delivery and continuous resilience or continuous verification or validation. The point is that it's automated and it's continuous. And I think that's the difference from the way we've been doing chaos engineering previously. So just to wrap up, as data centers migrate to cloud, these fragile and manual disaster recovery processes can be standardized and automated. Testing failure mitigation is going to move from this scary annual experience to automated continuous resilience. And we've been working on this at AWS. There's a paper you can find if you search for this title, Building Mission Critical Financial Service Applications. Pawan wrote the paper, I contributed some of it. And then there's this blog post as well. We've been working at AWS on services that support this, particularly multi-region. We have several database services now, Aurora and MySQL IDS and S3 that will copy data across regions for you. We've also made it easier to build multi-region CloudWatch dashboards, and we fixed a whole bunch of things that were just getting in the way, small feature enhancements to lots of services to make them work better in a multi-region environment. So if you're working on an application in this area, go see what we've got. If you're finding something that doesn't work or needs an update, then escalate it as a product feature request. Happy to be copied on those. I can maybe help find the right team to encourage people to fix it. But in general, AWS is always looking for feedback on what we need to do next. So I think that's it. Maybe we can go for some Q&A.
Yes, thank you very much, Adrian, for your clear and interesting presentation. If you still have time for questions, there is a first one. The first one is coming from Twitch. How much effort does an AWS customer have to deploy for continuous resilience?
I think if you're trying to start doing this, I would start with the people. So what the effort you'd require is, first of all, to have probably a manager with a goal is probably the best place to start. As an individual engineer, you can do some testing, but what you really want is an organization that cares about this. So I would start by finding a manager that cares about resilience, and who is on the hook if the system's down. What is the most valuable part of the system? Where are you trying to make this better? And there's probably somebody already in the organization. Once you identify them, I'd say, are you doing chaos testing exercises? Are you doing game days? Even if you do nothing to the technology you're running with, if you run exercises, you'll be in a much better shape, and it will surface all the places where you don't have good tooling, you don't have good dashboards, nobody knows what the login is to some system that's needed to resolve problems. So running those exercises is where I'd start, and from that will show you where you need to do more work. Ultimately, if this is important to you, you should have a dedicated person or dedicated team that is working to try and find the weaknesses in the system. So that would be the next step. And then there's some tooling you can get to help automate this. Obviously, there's Gremlin and Chaos IQ and Verica and a few others. And AWS is itself got some capabilities that you can use to help do this. And the other Adrian Hornsby has plenty of information. There's a little bit I have too. So I'd start with the people though.
All right. There is another question. Do you have anything to say about Cloud Act?
No, I don't know what that is. I'm sorry.
Right. Maybe if you check, you can add things to your question. Well, if you still have question for Adrian, you can send them directly in the chat. Adrian, if by any chance in the next months you come to France, I would love to have to organize a meetup with you. So, if you and your wife are coming, do not hesitate to contact me.
Yes, I'd be happy to come. Hopefully, I'm doing a lot of videos now. So the other thing is, if somebody particularly wants to have a discussion with me, I'd suggest you talk to your AWS sales team and the solutions architects and the account manager, and get them to get in contact with me, because I'm doing a lot of calls directly with customers right now. And that's mostly what I'm doing. So I'm spending less time in airports and more time on video calls.
Yeah, that's better. We just received a question from Patrick. What would be a reasonable overhead for continuous resiliency over normal operations?
If normal operations means that you go down fairly often, then you're looking at how much cost is it? What's the value of not failing, right? What you're trying to do is prevent failures. And we've seen that some extremely high cost of failure. So it really depends on the customer and the actual situation. What's the value of doing this? And then overall, if you get reasonably good at this, the system should cost less to run, because you're running with fewer failures and there's less expense around failures. So it should be part of the normal operation of the system. I wouldn't think that it's But as I say, probably, I'd say one person having it be their job to do this, that's kind of the overhead. Like if you're big enough that you can dedicate a person to it, then that would be where I'd start. It's a little bit like performance tuning. If you add a performance engineer, then they can probably reduce your cloud bill by more than the cost of the performance engineer, as long as you have a reasonably large, cloud footprint. It's a similar thing. It's as the value of your business gets to a certain level, it's worth justifying having people that will concentrate on availability.
All right. Thank you very much for the answer. For the moment, I don't have any other question, so maybe we can conclude the event. Once again, thank you very much. There is another question coming from YouTube. I know it's an answer from a previous question.
Okay.
Thank you very much, Adrian, for coming for today's meetup. It was a great pleasure to have you. Thank you very much to all the attendees and also to the speakers. Now I have have to say I wish you a very good holidays for this summer. I hope you could all have a nice rest. We'll probably have a new meetups in September, and I hope that these ones will not be virtual as the final we had this last month. Thank you, Adrian. Once again, thank you to Sebastian who helped me organize this meetup. I wish you all a very good day or night, depending on where you're based, and see you very soon. Goodbye.
Okay, thank you. Goodbye.